Hello guys, now in this video let's gonna talk about HNSW. HNSW stands for Hierarchical Navigable Small World. Okay, so mainly in this video I'm gonna cover these two topics. What is HNSW, why is it used, and how exactly HNSW works. Okay, now before you understand HNSW, let's understand where exactly it is used. So basically this HNSW is used in RAG. Okay, so in rag what exactly we will do. Okay, so there will be multiple documents. Okay, so there will be one query. Okay, so based on this query we have to fetch the similar documents. Okay, similar documents related to this query, and for fetching the top similar documents we use some algorithm called HNSW. Okay, so that's where HNSW comes into picture, and let's try to understand approximate nearest neighbor. Okay, so before you understand approximate nearest neighbor, so let's say, see, this is a query and we wanted to find the most top three relevant documents from these datasets. So what's the best thing that we can do? Okay, so we can go to one by one. Okay, so we can check the similarity. Okay, so we can check the similarity between this and this document and this and this document. So like that we can compare all the documents. Okay, and pick the top three documents from it. Okay, so that is basically nothing but k nearest neighbors. So basically in KNN what we will do is we'll check the every distance between every document and pick the top k documents from it. Okay, but in HNSW we don't do like that. Okay, so why? Because let's say here we have very less number of documents, but in a real world scenario there will be many documents. Okay, somewhere in billions or more than billion number of documents. So out of those many documents we need to find the top three relevant documents. So if we check one by one, that will take a lot of time to process. So that's the reason we use something called approximate nearest neighbor. Okay, so what exactly is this approximate nearest neighbor? So it will give you an approximate results. Like so let's say if we use approximate nearest neighbor on these, it will give you approximately three closest documents. That won't be the best three documents, but approximately those are the best documents. Okay, so basically ANN finds near optimal neighbors with very fast, like so this ANN will be very fast compared to KNN, but it can compromise little bit of accuracy. Okay, so one such ANN algorithm is nothing but HNSW. Okay, now let's gonna talk about HNSW. So HNSW stands for Hierarchical Navigable Small World. Okay, now for you to understand HNSW, you need to first understand what is navigable small world and what is skip list. Okay, so basically this HNSW is just combination of these two algorithms. Okay, now first we will try to understand this and then we will try to understand this. Okay, so first of all, what is navigable small world? Okay, so let's try to understand the concept of small world. Okay, so basically this is a really interesting concept, and this small world concept came from something called game theory. Okay, so in game theory there is one concept called 6 degrees of separation. Okay, now let's try to understand what exactly is this 6 degrees of separation. Okay, so what exactly it states is, let's say you can connect to any person in this world with just 6 steps. Okay, so that means let's say you are connected to Elon Musk with only just 6 steps. Maybe your relatives, friends, relatives, friend, maybe an Elon Musk. Okay, so like that what exactly it says is world is very small and you can connect to any person in this world in just 6 connections. Okay, 6 mutual connections. Okay. Now let's try to understand why this works. Okay, now let's say start with you. Okay, let's say if you have 50 friends. Okay, so and these 50 friends have some 50 friends. Okay, so total there are 2500 people. Okay, and again these 50 friends have one more 50 friends. Okay, so this basically, if you observe, it increases exponentially at every step. Okay, so after 6 steps it will be something close to 15.6 billion people, but if you observe there are only 8.3 billion people in this world. So that's why by this theory we can say that in at most 6 steps you can reach any person in this world. Okay, so this is one of the interesting theory, but of course if you have 50 friends and those 50 friends also have the same friends, so yeah, but if you observe it closely, this will work. Okay, so there are many theories why this works, but the intuition is this. Okay, so basically you can connect to any person in this world in just 6 steps. Okay, so this is one of the examples. So let's say if this is you and you want to meet one person else, so basically in 6 steps, so your friend maybe else. Okay, so after 6 steps, this is first step, second step, third step, fourth step, fifth step, and sixth step will be definitely the one whom you wanted. Okay, so this is the concept behind 6 degrees of separation. So basically what this 6 degrees of separation tells is our world is very small and we can reach in very number of steps. Okay, so that's the concept of small world. Okay, now let's try to understand what is navigable small world. Okay, now we will try to understand. Okay, let's try to understand how exactly this works. Okay, so basically this is like a graph. Okay, it will be having nodes and edges. Okay, now let's say there is one point. Okay, the query point, let's say q. Okay, and let's say there is some graph like this, and we wanted to find the closest node. Okay, there are many points like a b c d e, so consider these points as documents that I showed above. So basically here I showed documents, right? So these documents is nothing but some data points or nodes. Okay, so consider these as some data points. Okay, now our agenda is, if you got a new query point, how do you query this point, like how do you find the closest point to this query point. Okay, so for that how do we check is, let's say if we already have a graph like this. Okay, so first of all we will find there will be one starting point. Let's say starting point is a. Now we will find the distance between q and a. Okay, now let's say q and a distance is some 8. Okay, now again we will go to its neighbors. Okay, now again we will find the distance between q and these neighbors. Okay, now the distance is 7 and 4. The distance between q and these neighbors are 7 and 4. Okay, so if you consider the distance to a is 8 and its neighbors is 7 and 4, so it will go to the minimum. The minimum between these three is 4, right? So it will reach this point, and again from this point it will check its neighbors. We already checked this point, right? So it will check these 2 points. Okay, so out of these 2 points the distances is so the distance is from distance is nothing but 0.54 and 4. Okay, so out of all these points, this is the closest point. Okay, 0.54 is the closest point. Okay, so it will so this is how it will find the closest point. Okay, so basically what happens is at every step it will check its neighbors, and it will find the best one. Okay, and it will again check its neighbors, and then it will find the best one. Okay, so now let's try to understand how exactly this graph construction happens. Now I told about how this algorithm, navigable small world algorithm works. Now let's try to understand how this graph construction happens. Okay, now if you observe, sorry, now initially we will be having one point. Okay, now initially we will be having one point, and now if one more point comes, we will just attach these 2 points. Okay, and so basically this example is for inserting 5 data points, and that too here we took a parameter m as 2. Okay, now I will explain you what exactly is this parameter. Okay, now initially we will be having one data point. Okay, and now if one more data point comes, it will we will just attach this data point. Okay, now again let's say one more data point comes. Now we will check the distance. We will again start from here, check the distance between C and A. Let's say the C and A distance is 4, and we will check its neighbors. Okay, and its neighbors distance is 3.16. So basically the distance between B and C is 3.16. Okay, now it will find the top two things. Okay, the top two, like the minimum two things. Okay, so the minimum 2 data points are B and A, so we will connect to these 2 data points. Okay, now again now that we have this graph, now we let's say if one more point comes, let's say D, we'll again start from here. Now the distance between D and A is 5, and again we will go to its neighbors, and these neighboring distances are 4 and 1. So we will pick the top 2 best things, and we will connect it. So basically here if you observe, we are picking the top 2 best things, and we are for every new data point we are making 2 more connections. Okay, so that's the reason here m is equals to 2. Okay, so let's say if m is equals to 1, we will just pick the top best point, and we will just connect it to that point. Okay, but here if since we have top 2, we will connect the top 2 points. Okay, similarly for let's say if another data point comes, that is E, again we will start from A, we will check its neighbors, and see if you observe, the neighboring points are B and C, and again it will goes to C, since this is the smallest, it will goes to C, and again it will compare its neighbors. Its neighbors is only D, so basically these 2 points are the nearest ones, so it will connect to these 2 points. Okay, now see if you observe, in both the query and construction, we are just starting from one point and going to its neighbors and going to their neighbors, and just picking the best one out of all the ones. Okay, so this is how NSW works. Okay, navigable small world works. So if you observe carefully, this navigable small world is closely related to this small world concept. In this small world, so basically we are starting with one data point, and moving to its adjacent data points, and then again moving to its adjacent data points. Here I told something like we have 50 friends. This is something nothing but for this data point, let's say if we have 50 nodes, and again for that 50 nodes, again let's say if we have 50 nodes, something like that. Okay, so this concept is very close to this concept. Okay, so and the reason why this is implemented like this is because of this small world concept only. So due to this see, in this small world concept, we get to know that in less number of steps we can get the most optimal value. So here also we are doing the same thing. We are just checking the neighbors and their neighbors and their neighbors and so on. We are doing something like that. So basically here we are doing checking neighbors and their neighbors. So we can find in very less number of steps. Okay. So this is a concept of NSW. Now let's try to understand what are all the different parameters in this NSW. So first parameter is M, match number of connections. So this I already explained. Okay, so this is while constructing the graph. So basically there will be two parts. Okay, first one is construction and second one is query. Here you might have understand this point. Okay, so here we are inserting 5 data points. Okay, and then we are querying. Okay, so see, querying we will use when let's say if this is point Q and we wanted to find the closest point to this point, so that is nothing but querying. Okay, so but let's say if you want to frame this construct this graph, then it is nothing but inserting. Okay, now this match connections is a parameter used while inserting. Okay, while construction basically. So basically it tells how many closest points we need to pick and connect to the new data point. Okay, that is nothing but M. Okay, now there are two more parameters called EF construction and EF search. EF is nothing but exploration factor. Okay, now let's try to understand these two parameters. Okay. Okay, now so before you understand these two parameters, you need to have a basic idea on what is match heap, what is min heap, and what is breadth first search. Okay, so basically the see, breadth first search is nothing but, see, if you observe here, we are taking one point and we are iterating its neighbors. Okay, and we are picking the best neighbor, and then again we are repeating the process. So basically this is nothing but breadth first search. Okay, so basically we will in breadth first search we will go we will start from one point and we will search its neighbors and we will repeat that process. Okay, so this is nothing but breadth first search. Okay, and what is match heap and what is min heap. So I don't want to explain this in detail, but the idea is in match heap, let's say if you insert n number of elements and if you query a point, it will give you the match point. Let's say there is one queue, like in this queue we inserted like these data points. Okay, let's say there is one data structure, and in that data structure we added these 4 points, and if we just query a point, it will give you the match number. Here the match value is 7, right? So it will return you the maximum value. So min heap also does the same thing, but it will return you the minimum value. Okay, so basically this match heap and min heap are like containers. We can store elements, but if you query, it will give you the max element and minimum element. So let's say here now if I query, it will give you 7 as the result. Now if we query this, it will give you 5 as the result. Okay, so this is how match heap and min heap works. Okay, now let's try to understand these two parameters. Okay, now consider this example. Okay, now there is one query point. Okay, so see, this 10, 6, 8, 7, 2 are just the distance between this query point and this points. Okay, okay, so here these points are calculated using Euclidean distance like this. Okay, the calculations are done like this, but I'm not doing all the calculations and I'm just giving you the values. Okay, so basically the distance between Q and A is 10, QB is 6, QD is 7, and like that. Okay, now let's try to understand how exactly this NSW works. Okay, Now in NSW there will be two things, one is min heap and the other one is max heap. Okay, now initially we will start with A, right? So we will add this data point in both the heaps. Okay, so, now we will explore its neighbors. Its neighbors are B and C, right? Okay, now again since we explored this one, we will remove it from min heap and we will add its neighbors to the min heap, and again we will add its neighbor to max heap also. Okay, and see, in min heap if you observe these 2 points, this is the minimum thing, right? So min heap will give next time when we pop, min heap will give B as the result. Okay, so we will explore B's neighbors. Okay, B's neighbor is nothing but D, right? So here if you observe, first we have A, and we added its neighbors B and C into the min heap as well as max heap. Now we removed this B and added its neighbor, that is D. Okay, and same we added this to max heap also. Okay, now again let's explore D's values. Since see, now in the heap we have D and C. Out of D and C, which one is the minimum? D, right? Now remove the D data point and explore its neighbors. There are no neighbors, so we just remove it. Okay, now we have this data point. Okay, now we have C to explore. Okay, now C's neighbor is E. Okay, so we will add E to again both the min heap and max heap also. Okay, here we considered EF as 5. See, this EF exploration factor that I discussed here is nothing but this heap size. Okay, this heap size is nothing but exploration factor. Okay, now this reached the maximum value. Okay, now if you observe and now we have E in the heap, right? Now we will again find these neighbors. Okay, here we don't have any neighbors, so this is basically a empty thing. Okay, now if you observe the final max heap, we have all these points. Okay, and basically the best of this one is nothing but E. Okay, and if you observe the best one is nothing but E only. Okay, so the minimum point is E only. Okay, so we got the best point. So here you might have got two things. See, here first of all let's try to understand why exactly we are using min heap and why exactly we are using max heap. Okay, see, this min heap is used for exploring the minimum data points. See, see, I said we will start with 1 point and we will check the neighbors, and again we will check the neighbors, right? So while checking the neighbors, we need to know which one is the minimum point, right? So for tracking the minimum point, we use a min heap. Okay, now why do we need max heap? So basically the result that we get is from max heap only. So the last 2 points that are there in max heap is the last 1 point that is there in max heap is nothing but our result. Okay, here the last point that is there in max heap is E, right? So E is our result. Okay, so we got the best result. See, here I am using EF is equals to 5. That means this max heap size is 5. Okay, now I will tell you why exactly we need this exploration factor and what happen, what advantage we will get. See, now in by this algorithm we got the best value as E, right? Now let's say if I follow the same algorithm that we used here what I said, we need to start from this point and we need to check the neighbors and we need to check the pick the minimum point, and we need to repeat that process, right? So let's say if we use the same algorithm here, so basically we will start from here. So which one is the minimum? So out of B and C, which is the minimum? B is the minimum, right? So we will go here, and what are its neighbors? Its neighbors is D, so we will go here. So if we use this algorithm, okay, we will get this as the answer instead of this. Okay, so we will get D as the answer instead of E. Okay, and the reason for that is this is nothing but local minima. See, there are basically two branches for it. So the problem we have is here it is getting stuck with the local minima, but we need global minima. So see, for getting the global minima we use something called exploration factor, and how this works I already explained. Okay, so if you use this exploration factor, BFS kind of search, then we are getting the minimum value. And not on, and what exactly is this number? Okay, here I choose exploration factor as 5. Okay, see, if you choose exploration factor as 1, then it boils down to same thing. Okay, see, now let's say if I consider exploration factor as 1, then in this match heap we will be having only one element, so we will search only one element. Okay, now we will get only it's same algorithm that I explained before, like starting from here, going to its neighbor and going to its neighbor. So if we keep EF is equals to 1, we will get this answer, but here since we gave EF is equals to 5, we got this answer. Okay, I think I made myself clear. And now let's say, what if we give the smaller EF value? Okay, let's say take EF is equals to 2. Okay, now what happens? Okay, let's say if EF is equals to 2, first we will start from here. Okay, initially in min heap and match heap we will be having a data point, and now we will go to its neighbors. Its neighbors are B and C, so we will add these 2 points in these 2 points. Okay, and see here, if you observe, in the previous example we added 3 data points. Okay, A, B, C. Okay, but here we given EF is equals to 2, that means the maximum limit of this is only 2. So what we will do is, what this match heap does is, so it can give you the maximum value, right? Here the maximum value is 10 and the candidate values are 6 and 8. So see, this 6 and 8 are lesser than this match value, right? So it will just pop this value and it will add these two values. Okay, now again now also this heap is full. Okay, now again we will check this min heap thing. Okay, now the minimum value is B, right? And B's neighbors are D, so we will remove B and add D to it, and we will add D to this also. But the point is here this is filled, so what we will do again, here the maximum value is C, so we will remove C and add D. Okay, why we are doing like this? Because here C distance is 8 and D distance is 7. D is better than C, right? So we are adding this and removing this data point. If it is not better, we won't remove this. Okay, since it is better, we are removing this and adding this point. Okay, and again since for D we don't have any data points to explore, and again see, for now we have C in the min heap, but we don't explore C. Why? Because I will tell you why. See, in C we don't check the C's neighbors, unlike here after C we checked its neighbors. Okay, we checked its neighbors, that is E, and we added it to min heap, but here we won't do that. Why? Because see, this 8 is even greater than this 7. Okay, see here these are the best candidates we got. Here we are only considering the two best candidates. Okay, this is even worse than these two best candidates that we got. So see, what this algorithm thinks is it is not worth looking at this point. Okay, so even if you look at this point, you won't get the better result than this, so it will basically ignore this data point. Okay, See, so we will again end up with the answer 7 only. So here the point I was trying to make is this exploration factor we need to set is as maximum as possible to get the best results. Okay, then why don't you set the very bigger value? The thing is, if you set the very big value, we have to explore many points, the computation will increase. Okay, so basically what exactly is this exploration factor denotes? Maybe by this point you might have understand what exactly is this exploration factor. Basically that is nothing but this node, this math heap is nothing but that exploration factor number that we are specifying. So basically what it says is number of promising nodes the algorithm is allowed to track. Okay, so basically if we say exploration factor as 2, it will track the two most promising nodes. Okay, here we have two most promising nodes as D and B. See, this node is even worse than the promising nodes. Okay, so we are not checking this node. Okay, but so that's the point, it will only check the two most promising nodes. So that's the main point. See, if we set this a very huge number, we need to keep track of many promising nodes, and these iterations will increase, and this will take lot more time. So we need to have a balance between this. Okay, it should not be very small. If it is very small, it will stuck in local minima. As I said, if it is even 1 or 2, it will stuck in local minima, or if it is greater than 2, it won't stuck in the local minima. And this is for this particular example. So we need to make it as big as possible, but it should not be very big. Okay, so this is how the navigable small world algorithm works. Okay, so basically it is kind of BFS algorithm. So basically we will check its neighbors and its neighbors. So that's how navigable small world algorithm works. Okay, now let's talk about the part 2, that is skip list. Okay, so here I talked about two things, right? See, this HNSW is just a combination of two things, that is navigable small world and skip list. Now we discussed about this navigable small world. Now let's come to skip list. Okay, okay, now let's come to skip list. Okay, so see, this skip list is some interesting data structure. Okay, so it's like a linked list only, but the thing is in see, let's say we have these data points. Okay, 3 6 7 9 12 17 19 21 25 26. So these are the data points we want to insert to this particular skip list. So how it is done is, so there will be multiple levels. Okay, so in level 1 we have all the data points. So we have these data points, so we will be having all the data points. In level 1 we will be having only few data points. Okay, compared to this data point we will be having less number of data points, and in level 2 we will have even less number of data points, and in level 3 we will have even less number of data points. Okay, so this is a this skip link list is constructed. Now let's say if there is one data point. Okay, now we need to search for 19. Okay, see, if you observe these two algorithms in either navigable small world or skip list, first we will construct one tree. Okay, and then we will query with one data point. Okay, so this is the thing. So even in drag also we will do the same thing. First we will ingest all the documents, and we will do the query thing. Okay, so the same thing applies here also. Well, now see, now we have now let's say in this data structure, that is skip link list, we wanted to search 19. Okay, we wanted to search this number. Now let's try to understand how exactly this search works. Okay, now first it will start with 3. Okay, now after 3 it will check, it will go to next node. Okay, next node is 17, right? Now it will check whether 17 is less than 19. Yeah, 17 is less than 19, right? So it will move forward, and the next node is infinity. Okay, so infinity is not smaller than 19, right? So it will go down. Okay, now again, so basically first it will start with 3, it will go to 17, and it will go down, and the next one is after 17 it is 21, right? Now it will again check, is 21 greater than 19? Yes, 21 is greater than 19, right? So it should be somewhere between 17 and 21. So again it will go down. Okay, now it will again check what is the next one. Next thing is 19. So we got the 19. Okay, so within just 3 steps we got 19. Instead of searching linearly one by one, this is a very fastest approach. Okay, so basically it will in every level it will go one by one, it will go like this, and if anything greater than this set square is found, it will go down. Okay, so that means, let's say see, we are at 17, and the next node is 21, so the result is 19. So that means it should be somewhere in between these two things, right? So that's why it is going down. Okay, now this is how this skip list works. Okay, now this is also faster because here we are taking less number of steps. If we search manually, it will take lot number of steps. Okay, we need to search 3, 6, 7, 9, 12, 17, 19, so lot many steps. We are doing it in less number of steps. Okay, now the question comes is what in level 1 what elements we need to choose, in level 2 what elements we need to choose, and in level 3 what elements we need to choose. Okay, see, it's not okay. So for that, what we will do is this is kind of very interesting. So what exactly we will do is, one second, yeah. So here we will start with, it's like flipping a coin. Okay, now we will just flip a coin. Okay, if it is head, we will just go forward. Okay, and we will repeat that process till we get the tail, and as soon as we get the tail, we will insert in that level. Okay, see, consider this example, consider 3 we got a head, tail. Now see, after 3 steps we got tail, right? So we will keep it in third level. Okay, now consider 6. So first one itself is tail. Okay, now so we inserted it in 0th level. Okay, now consider this one. So after 2 heads we got tail. Now so we will insert it in second level, and consider 9. After 1 head we got tail, so we will keep it in first level. So like that, according to this, so basically we are just flipping a coin, and after how many times we get the tail, so in that level we will insert. So if you observe the probabilities, see, first initially if you get the tail, we will insert it in level 0, right? So what is the probability of getting tail? It is just 1 by 2, right? Okay, now what is the probability of inserting going to level 1? Okay, so that is nothing but 1 by 2 into 1 by 2. Okay, so that is 1 by 4. Okay, so the probability of reaching level 2 is nothing but 1 by 2 into 1 by 2 into 1 by 2. So basically probability of reaching to level L is nothing but 1 by 2 whole power of L plus 1. Okay, so so this is how we will do. And why exactly are we doing like this? So see, probability of getting head in first tail in first attempt is you know, if we get a tail in first attempt, then we will place it in level 0, or else if we get after 2 steps, we will place it here. So if you observe, the probability of reaching to third level decreases. If you observe, the probability is 1 by 16, which is very less. Okay, so the in level 3 we will be having less number of nodes, and in lower levels we will be having more number of nodes. So this is how this works. Okay, so here, since we use here, this is nothing but promotional probability. Okay, here see, the for flipping a coin, the probability is 1 by 2, right? That 1 by 2 is nothing but a promotional probability. Okay, now what does this promotional probability 1 by 2 signify? Okay, so that means in this level, let's say if there are 10 data points, so what this promotional probability says is, in next level we should ideally have only 5 data points. So if you observe here, so promotional probability of 2, what it signifies is, in 0th level we should ideally have 10 data points, and in first level we should ideally have 5 data points, and in second level we should ideally have 2.5 data points, like that. Okay, so this is what that promotional probability signifies. Okay, now again, here these are the actual values and these are the probability values. Okay, actually ideally it should be like this, but now in this particular example it is like this. Okay, now this is how it works. Okay, now actually there are 2 probability levels. Okay, first one is probability that the highest level is exactly L. Okay, see here, P of level is equals to L is 1 by 2 whole power of L plus 1. So what exactly is this probability? Is probability that the highest level is exactly L. Okay, see, what is the highest level of 3? That is 3, right? So the probability that the highest level is 3 is nothing but 1 by 2 whole power of L plus 1. That is this probability. Okay, see, the probability that the highest level for the 7 is 2 is nothing but 1 by 2 whole power of 2 plus 1. So 1 by 2 whole power of 3. Okay, so that is the probability of highest level exactly L. Okay, probability of highest level for this particular element to be exactly 2 is nothing but P of L plus 1. But there is one more probability also, that is probability of being present at level L. So see, this probability is completely different. So what this probability signifies is, in this level, what is the probability of having elements? Okay, see here the probability of having elements is 1. Okay, that's because all these elements will be present in level 1. Okay, so here the probability is 1. Okay, so we will definitely find an element in level 0. Okay, but here the probability is 1 by 2. Okay, this is different. Okay, see what this signifies is, what is the topmost level for these elements. Okay, see, if you observe, see, as I said, ideally here in level 1 how many elements are there, in level 0 how many elements are there? Exactly half number of elements should be there in level 1 according to the probability. So that means if you observe, half of the elements half of the elements highest level will be this only. If you observe 6, 12 and 26, these data points highest level is level 0 only, and so ideally it has to be half. Okay, here we have only 3 elements, but ideally it has to be 5 elements. Okay, so basically that's what this probability signifies. Okay, probability of this probability of being level 0 as highest level is 1 by 2, whereas this probability, what this signifies is probability of element, finding this particular element in this level. Okay, so probability of finding this particular elements in this level is 1, because whatever element you take, you will get find in this level. Okay, here probability of finding these elements in level 1 is 1 by 2. That's because only half the elements will be there in this level, and this will be 1 by 4, and this will be 1 by 8. So basically, as I said, probability of level 0 is 1, 1 by 2, 1 by 4, 1 by 8, 1 by 6. So here the probability is p power l. Here the probability is p power l plus 1. Okay, don't confuse. Okay, now for see, in HNSW we use this promotional probability as 1 by m. Okay, now see why we use 1 by m. See, I already mentioned what exactly is m, right? M is nothing but maths connections. Okay, now let's say if we insert a new data point, so what are the maximum number of connections? Okay, so for that one, so basically what it signifies is, if a number of m is equals to some 5, we need to have 1/5 of the elements in the next level. Okay, and we need to have 1 by 25th number of elements in the level 2. Okay, so that's what this signifies. So basically, in skip list we use promotional probability as 1 by 2, but in HNSW we use a promotional probability as 1 by m. Okay, now this is the code. Okay, so basically we'll just generate a random number, and if it is less than this promotional probability, we will increase the level. So it's just like flipping a coin. Here I told, right? So we'll just flip a coin. So see, if you flip a coin, the number can be it can be head or tails, right? So here also same thing. This random number can be any number between 0 and 1. So if it is less than p, that's like it is head. Okay, if it is greater than p, that it is like tail. Okay, so this code we will use, but in HNSW we will use some some optimal number. So basically, if you use this formula, we will directly get what level it is. Okay, instead of iterating with while loop, if you use this formula, we will directly get the answer. So here in P, for skip list we use 1 by 2, and for HNSW we use 1 by m. Okay, that's what we need to remember. Okay, so now we understood about skip list also. Now let's talk about HNSW. So as I said, this HNSW, so as I said, now let's go back again. See, this HNSW is just a combination of navigable small world and skip list. Okay, now we discuss these two, navigable small world and skip list. Now let's discuss HNSW. Okay, okay, now yeah, so basically, see, this is one navigable small world. Okay, and this is one more navigable small world. So this HNSW is like this. Okay, here also we will be having multiple levels, same like skip linked list, and each level is nothing but NSW, navigable small world. See, here each level is single linked list. Okay, but here each level is NSW. Okay, now see, similar to that, in top level we have less number of nodes, and in bottom level we have more number of nodes. Okay, and this increases gradually. Okay, and in what rate it will increase? So basically, if we have 2 nodes here we have 2 into m number of nodes. Here we have 2 into m number of nodes. as I said, for HNSW p is equals to 1 by m, so that's how it will be. It will increase with m number of times. Okay. So okay, I will explain with an example like how exactly this HNSW works. Okay, now let's say there is some graph like this and we have some query data point. Okay, so this numbers, as I said, 30, 20, 25 is nothing but the distance between query point and this point. Okay, let's say the query point is q. Okay, so query point is q, and okay, let me take one. Okay, let me explain it. See, 1 second. Oh yeah. Okay, so let's say query point is q. Okay, 1 second. Okay, now let's say the query point is q, and from this query point we need to find the minimum element in this graph. Okay, so we will start with this point. Let's say n1 is the entry point. Okay, so we will start at this point. Okay, now we'll check its neighbors. Okay, its neighbors are n2 and n3, so its distances is 20 and 25. Okay, so compared to 30, 20, 25, which is less? 20, right? So we will go here. Okay, so in this layer, in this NSW, so this is one NSW. Okay, this entire thing is one NSW. Okay, so in this NSW we got the minimum element. Okay, now we will go down. Okay, we will go down. See, these points are always connected, these and these and these. Okay, so these and these are connected basically. Okay, these and these are connected. Okay, okay, so same point will be connected to the same point in down layer. Okay, except in down layer we have even more points. Okay, how many more points we have? It is m times more points we have in the down layers. Okay, now since we got the minimum point here, we will again go down. Again we will, here also we will do the same thing. Okay, so we will start from here. So we will check the neighbors. So what are the neighbors? This and this and this. These three are the neighbors. Okay, so out of these three, out of these three, so 15 is the minimum, right? So 15 is the minimum, so it will come here. Okay, so if you observe, 1 second, so here 15 is the minimum. Okay, so for 1 second, let me use one more color. Okay, so here 15 is the minimum. Okay, so we started from here, we checked its neighbor. So here 15 is the minimum, and again from here we will check its neighbors. What are its neighbors? Its neighbors are only this point. Okay, so and this is minimum, right? So again we will start from here and we will check its neighbors. Already this we checked. Okay, so 12 neighbors are 18 and 17. Okay, so we already checked 18, like 18 is already visited, so the only neighbor is 17. So out of 17 and 12, 12 is minimum, right? So in this NSW, so basically in this particular NSW, the minimum one that we found is this one. Okay, so we need to again go down. Okay, now we will come here. Now we will check the neighbors. The neighbors are 10 and 7. So out of these three, which one is minimum? This is minimum, so it will go this side. Okay, and so again its neighbors are this already visited, so this. So out of 7 and 5, this is minimum, right? So finally it will reach here. So in this way, for this particular query point, this will be the minimum point. Okay, so if you observe all the values, So 5 is the minimum point, right? And using this HNSW also we found 5 as the minimum point. Okay, so yeah, so if you observe here we have 3 NSWs. This is the first NSW, okay, and this is the second NSW, and this one is the third NSW. Okay, now let's go forward. Yeah, and there are two more parameters that we didn't discuss, that is mmaths and mmaths 0. Okay, now what exactly is mmaths and what exactly is mmaths 0? So let's try to understand it with NSW and HNSW. See, in NSW and HNSW there is one small difference. Okay, so basically I said every layer is NSW, right? But there is some mild difference. See, in NSW a node can have many number of connections. Okay, see, but here that is not the case. Okay, in HNSW a node can't have many as many number of edges. Okay, so if you observe here, let's say if you go back and try to understand NSW, see here m is equals to 2, right? So if we keep m is equals to 2, so at this stage if you observe for this particular node, okay, let me show you. See, for this particular point we have 1 2 3 4 edges. Okay, okay, so here actually m is equals to 2 only, but we have 4 edges. Okay, sorry, yeah, 4 edges. Okay, yeah, so the point I was trying to make is here m value is 2 only, but number of edges for this particular point is 4. But so in NSW there is no restriction. Okay, a node can have any number of edges, but in HNSW that is not the case. Okay, so see, in NSW we can have any number of nodes, but in HNSW there is one restriction. In all the top layers a node can have at most only m number of elements. Okay, so if m is equals to 2, so at most this particular node in the top layer can have only m connections. Okay, not more than that. And in layer 0 it can have 2m number of edges. Okay, so see, that's because in the lowest layer is very much important for searching. So this HNSW algorithm is a little bit legitimate, that for layer 0 it will consider it as 2m, but for all the top layers it will restrict it to only m. Okay, but in NSW there is no such restriction. For any node we can have any number of edges. Okay, so if they so while inserting, if we came across more than m edges or more than 2m edges here, it will just remove some of the edges which are very far apart. Okay, so see, basically these two parameters signifies that value. Okay, so there is one parameter called mmaths. This mmaths signifies how many maximum number of connections the top layers can have. Okay, so usually its value will be m. Okay, so this mmaths 0 signifies how many maximum number of connections allowed for layer 0. Okay, so usually this number will be 2m. Okay, now so this is the difference. So for NSW we can have unlimited number of connection, but for HNSW it is bounded, m for layers greater than 0 and 2m for layer 0. Okay, so this is the case. And also, yeah, so one more thing I wanted to say. So this is the whole reason. See, this is the whole reason of picking P as 1 by m. So the connection is See, we have at most, if you ignore this particular last layer, for all the other layers, the connections will be at most m, right? So, since the maximum connections are at most m, if we just, to layer, if the number of nodes becomes, 1 by m, the density becomes the same. Okay, so here if you observe, see here for every node we will be having at most m nodes, and here in this layer, if we just reduce it by half, that that doesn't satisfy the case. Okay, so if we reduce it to 1 by m, like let's say if we, here the m value is 10, and here if we have 20 nodes, here we need to make it as 20 by 10, that is only 2 nodes only. So if you make like that, then the distribution will be proper. Okay, so that's the whole point of choosing p as 1 by m. Okay, so yeah, so this is all about HNSW, and thank you.